Welcome to The Explainer, everyone. I am absolutely thrilled you've joined us today. You know, if you're the kind of person who just loves peeling back the outer casing of complex industrial machinery to see exactly how things tick on the inside, well, you are definitely in the right place. Today, we're setting the stage to explore a true mechanical unsung hero of industrial precision. We are talking about the gearbox mechanics inside RF, or radio frequency electrode positioning systems. These are heavy-duty components. We're talking about weights comparable to a small car, yet they have to move with the absolute microscopic precision of a Swiss watchmaker. We're going to look at how raw rotational energy is essentially tamed and then transformed to do some incredibly heavy yet highly delicate lifting. Let's get right into it.
So think about this absolute engineering nightmare for a second. How do you move massive, incredibly heavy metal plates, but do it with the delicacy and precision of literally a single millimeter? It kind of sounds like a contradiction, right? Usually you've got machinery built for brute strength, stuff that just smashes through whatever's in its path. Or you have machinery built for microscopic precision, operating in clean rooms with tiny, tiny payloads. Doing both of those things at the exact same time, that is the high-stakes challenge of a large-scale RF dryer. And the elegant, powerful solution to this heavy-duty problem, it all comes down to the humble gearbox.
Okay, let's dive into this. Before we talk about the physical movement of these massive plates, we've got to quickly recenter on the critical variable we're actually trying to control here, the air gap. As we know, modifying that adjustable space between the top electrode and the wet product is what directly regulates the RF power density and the overall drawing rate inside the entire machine. It's not exactly a new concept for us, but it is, without a doubt, the single most critical variable in the whole process. Because if that gap is off by even a fraction, you're either going to scorch your product completely or you're going to leave it soaking wet.
So let's trace exactly how this builds our understanding of the machinery itself. To properly control that air gap, we need a highly reliable, highly repeatable motion. We're looking at the chronological journey of kinetic energy here. We're going to trace exactly how energy transforms from pure, high-speed rotational power at the source all the way into a highly controlled, incredibly strong linear force at the destination. Think of it like an elegant mechanical relay race where the baton being passed is just pure torque. And here is that step-by-step mechanism laid out clearly, which applies whether you're operating a massive textile dryer or running an industrial-scale food processing plant. Step 1 in our relay race is the power input, an electric motor. Usually, this is a servo or a stepper motor. This motor feeds power directly into Step 2, our gearbox, which acts as a speed reducer, commonly a worm gear or a helical gear setup. Once the gearbox works its magic, its output shaft drives Step 3. That's going to be your ball screw, a lead screw, or a rack and pinion system. Finally, as that screw turns, we reach Step 4. That massive plate-like electrode is pushed up or down, creating precise linear motion right over your product. Now, what's really interesting about this slide is the stark contrast between the start and the end of this mechanical journey. On the input end, the motor generates high-speed but low-torque rotational energy. It's spinning super fast, but it doesn't actually have the lifting force to move that heavy plate on its own. But then, on the output end, the final electrode movement is slow, precise, and features high-torque linear motion. The mechanical magic happening right in the middle, thanks to the gearbox, is torque multiplication. It drastically slows down the rotation speed of the motor to vastly increase the mechanical lifting force.
Which brings us to Section 2, why gearboxes are critical. We've looked at the pure mechanics, but let's zoom out for a bit. Why is this specific setup so fundamentally critical to the operation of an RF dryer? Let's take off our theoretical physics hats for a moment and put on our applied engineering hats to really understand the real-world implications of this design.
And this brilliantly illustrates the 4 primary reasons why the gearbox is the undisputed muscle and grains of the entire RF drying machine. Precise impedance matching, overcoming heavy loads, self-locking safety, and automated control integration. Without the gearbox fulfilling these 4 exact functions, the whole RF drying process would literally grind to a halt. Or worse, it could become dangerously unstable and completely fry your product. So let's break these down one by one. First up is precise impedance matching. The crucial point here is that the RF system requires minute height adjustments to perfectly match electrical impedance. We are not talking about moving the electrode a few inches, right? We're talking about moving it in fractions of a millimeter. Because the gearbox has such an extremely high gear ratio, we are talking about ratios sometimes exceeding 100 to 1, it allows the control system to translate that fast motor spinning into these microscopic, highly precise height adjustments. This is absolutely paramount for the electrical stability of the entire system. Without that 100 to 1 reduction, you would overshoot your target impedance every single time.
Next up is the sheer brute strength required. RF electrodes are massive metal plates. I mean, they are incredibly heavy. These plates don't just have weight, they have the kind of mass that would snap a standard actuator like a twig. As we saw earlier, the motor alone just does not have the torque to handle this. The gearbox provides the raw, unadulterated muscle needed not only to lift this massive weight up and down, but to hold it perfectly steady at the exact fractional millimeter required without slipping or putting any strain on the motor.
But what happens if something goes wrong? The stakes here are incredibly high. Just imagine a massive, insanely heavy metal plate suspended right over your wet product, and suddenly, boom, the facility loses power. The motor shuts off. Gravity takes over. You would totally expect that heavy electrode to just come crashing down, right? But it doesn't. Many RF dryers use worm gearboxes specifically because worm gears are naturally self-locking. This mechanical property prevents the heavy electrode from crashing down if the motor loses power. It acts as an instant, completely mechanical failsafe that doesn't require a single drop of electricity to keep your machinery and your people safe.
Finally, the gearbox doesn't just operate in a vacuum. It acts as the physical actuator for the machine's digital brain. It seamlessly works with automated PLC feedback loops. For example, let's say an internal current sensor detects way too much power inside the machine. The PLC instantly tells the motor gearbox assembly to act. Because of that direct, geared connection, the system can instantly lift the electrode to widen the air gap and immediately stabilize the power levels before any damage actually occurs. It's this continuous, real-time conversation between the digital sensors and the physical gears.
So, we've seen how the gearbox acts as a torque multiplier, a precision instrument, and a self-locking safety net all at the exact same time. It is honestly fascinating how a seemingly simple gear arrangement can be the linchpin for complex, automated electrical processes. Which leaves me wondering, what other automated mechanical failsafes are silently protecting industrial processes around the world right now? Thanks for joining me on this explainer. Keep asking those great questions, and I'll catch you next time.